Hello, welcome to Chapter 20 Notes on Electrochemistry. Here are some examples of electrons doing work. That's what electrochemistry is all about. In fire, the wood is oxidized to produce lots of energy for heat, rusting, bioluminescence, batteries, some awesome glaze making in pottery, raku, oxidation of food, which helps it decompose, and oxidation of metals, along with some pretty cool solar power. Okay, chemical reactions in which the oxidation state of one or more substances changes are called oxidation reductions. I like to call them redox, a little bit shorter. You've heard me give you the acronym. Oil, oxidation is loss. Rig, reduction is gain. Or alternatively, Leo the lion says grr. Loss of electrons is oxidation. Gaining electrons is reduction. So oil rig or Leo grr. Electrochemistry is a branch of chemistry that deals with the relationship between electricity and chemical reactions. All right, for example, if you had zinc added to hydrochloric acid, you would spontaneously get zinc ions and hydrogen gas. That's a redox reaction. The zinc has changed its oxidation number from 0 to +2, and the hydrogen has gone from 1 to 0. Zinc is oxidized because it lost the electrons, and hydrogen is reduced. Hydrogen causes zinc to be oxidized, and therefore you call it the oxidizing agent. Zinc causes hydrogen to be reduced, therefore it's the reducing agent. Here's another example of oxidation reduction with zinc with oxygen.
When zinc metal is exposed to oxygen at high temperature, it reacts to form zinc oxide. Electrons are transferred from zinc to oxygen, creating oxide and zinc ions. We say that zinc has been oxidized. The oxidation of zinc by molecular oxygen is an example of an oxidation-reduction reaction. More generally, oxidation corresponds to a loss of electrons. Zinc is oxidized because it loses electrons to the oxygen. On the other hand, oxygen is said to be reduced because it gains electrons.
All right. Now, the law of conservation of mass works well for balancing oxidation-reduction reactions as well. So we need to also pay attention to balancing electrons. It gives you a little bit easier, in my opinion, way of balancing the reaction. So balancing the atoms and the charge. So we're going to go through a balancing equation, a redox balancing equation. There are some steps involved that don't necessarily have to be done in the order that they're described here, but could be done in a different order. But you got to start somewhere. So here we go. You want to start by separating the oxidation and the reduction. Helps you focus on the electrons. So here we have a reaction in which iron 2+ is reacting, tin 2+ is reacting with iron 3+ to make iron tin 4+ and iron 2+. The oxidation is the tin losing electrons. The reduction is when the iron gains those electrons. Now notice the iron atom only gained 1 electron, but since we need 2 electrons to be gained and lost, since tin lost 2 electrons, you're going to need 2 irons. So right there you can see that the electrons balance along with the atoms. Okay, whoops. So let's practice one. This is one that you did in your lab. So pause, because I don't have. Okay. So hopefully what you have from the lab is the copper 2+ ion reacting with zinc metal to produce zinc ions plus copper. That's the overall reaction. The oxidation is going to be where the electrons are lost. So the zinc is the one that is oxidized. So zinc with a 0 charge, I'll just put that there to help you see that, yields a zinc 2+ plus 2 electrons. You don't ever subtract electrons. So the reduction, therefore, is going to be the copper 2+ ions gaining those 2 electrons to produce copper. Seemed like most of you got that in the lab. All right, so now a little bit more complicated reaction. This is a reaction that we're going to be doing in our next lab, where we're titrating hydrogen peroxide with permanganate. In this particular example, it would be titrating sodium oxalate with potassium permanganate. The permanganate is reduced to Mn2+, which is very pale pink, and therefore you get the indicator color, while the oxalate is oxidized to carbon dioxide. All right, so balancing this reaction is a little bit more challenging if you're just trying to figure out all the atoms. So here's how we can do it. First, let's break it down into 2 incomplete half reactions. The MnO2 yields Mn2+. The C2O4 yields CO2. So those are the basic half reactions. Now, how do you know which one's being oxidized and which one's being reduced? One thing you can do to help you decide what's happening is assign oxidation numbers. In this case, we did this earlier in the year, but oxygen is one you can always count on to be a -2 unless it's in a peroxide. So if that's -8 total, we have a leftover -1 that leaves the manganate as +7. So if we know it's changing to a +2, that has gained the electron, so this is the reduction. Okay, in this case, if we call oxygen -2, we'll call this carbon a +4. Here, -2, that means a total of -8. Overall left remaining charge of 2-. So this needs to be a +6. There's 2 of them. So each carbon has a 3+ charge, going from +3 to +4, meaning it lost electrons and it got oxidized. Okay, so after we have the half reactions, we should first balance atoms other than hydrogen and oxygen, because that has to do with acids and waters and things. So first, okay, the Mn's are balanced. Now we add a 2 coefficient to the carbon dioxide and the carbons are balanced. Okay, now you can balance the oxygens by adding water, because this is an acidic reaction, so the acid hydrogens, are going to react with the oxygens to make water. So in the first reaction, you're going to be able to make 4 water molecules because you have 4 oxygens. And in the other reaction, the oxygens are already balanced. Okay, next step. We got to balance those hydrogens. We know it's an acidic reaction because we're focusing on acidic reactions in general. So we need 8 hydrogen atoms to balance out those 4 water molecules. Now it looks like in this half reaction, all of the atoms are balanced. and the other one was already balanced. Okay, so next we have to balance the charge by adding electrons. Now in this case, we had already determined that this was a +7 and this was a +2. So there's a difference of 5 there. So we'd add 5 electrons to reduce the manganese. You could also figure that out by knowing that there's 8 positives here and a -1 here with a +2 over here. To get these two to be equal, you need to add a -5 from the 5 electrons. So -6 + 8 is +2, and that's what you have there. Okay, and the other one, we also knew that, that this was going to be a +3, and this is a +4. We have 2 carbons losing 1 electron each, so that gives you the overall -2 electrons. And again, you can see the charge of a -2 to a 0. You're going to have to balance those 2 negatives. 2 ways to look at it. Okay, now we're going to multiply each half so that the number of electrons are equal. So we had 5 in the reduction and 2 in the oxidation, so a common multiple of 10 gives you this reduction half reaction and this oxidation reaction. So this top one was multiplied by 2. All of the coefficients had to be multiplied by 2. And here the coefficients had to be multiplied by 5. Now we can see that the electrons will cancel out and we can put them together into our overall balanced equation. That wasn't too bad, huh? Again, you don't have to do it in the order in which I did it. It works if you start with the electrons and then add in the oxygens and hydrogens. It works the way I just showed you. Okay, another type of common oxidation reaction is something happening in a basic solution. And we're pointing these out specifically because you have to add waters and hydrogens when you've got a pH change involved. Now, if you're doing a basic solution, you do the same process that you did in the one before, except you add hydroxides to neutralize the hydrogens that are used rather than water molecules, because you know that you need a basic solution in the end, or you're starting with a basic solution. So one example would be potassium iodide added to potassium manganate 7 solution under alkaline conditions. A brown precipitate is obtained. Write the ionic equation for this reaction. Okay, that should be potassium permanganate. This is the balanced equation. Feel free to play with that if you'd like. I'm not going to take the time right now to go through that step by step. We'll do lots of these in class starting on Monday. Okay, so let's talk about voltaic cells, the other part of what we did in class on Friday. Here's a voltaic cell, very, very similar to what we created. We had a zinc solution, a zinc electrode, copper solution, and a copper electrode. The energy released in the spontaneous redox reaction can perform work. We saw it show a voltage. We could have put a light bulb in here and lit the light bulb, and with enough current flowing, we could have run a fan or, run other electrical devices. So these are called voltaic or galvanic cells. and they are devices in which electron transfer occurs via an external wire so that the electrons can do some work for us. They use spontaneous reactions because when the metals or elements of different activity levels sense each other through the wire, they will spontaneously have electrons flow. And yeah, here's the example that we did in lab, and we did indeed see that electrons flow and work was done and copper was deposited. Okay, some basic vocabulary. The anode was the zinc because oxidation takes place at the anode, both vowels, anode, oxidation. Cathode is where reduction takes place. Gave you that example in class of how to remember that one. And you have to have a salt bridge to complete the circuit so that the charge can stay balanced. The cations move from the anode to the cathode, and the anions move from the cathode to the anode. And lastly, the two solid metals are the electrodes, called cathode and anode. As oxidation occurs, the zinc is converted to the zinc 2+ with 2 electrons, and the electrons flow toward the cathode through the wire, where they are used to cause the reduction to happen. And that's where the copper electrodes gain electrons and therefore gain mass by reducing those copper ions back to copper metal. Electrons always flow from anode to cathode alphabetically, A to C. And therefore the anode in chemistry is given the negative sign because the electrons are flowing from there to the positive cathode. That works well. Cathodes are like positive cations, and the electrons are attracted to it. Electrons can't flow through the solution. It has to go through the wire. That's where the electrons are able to flow. They're not able to be carried around in the solution. The charged particles, the ions, can flow, but not electrons by themselves. All right, so here's another picture of a galvanic cell. Anode, electrons flowing to the cathode. You have to have ions be able to flow through a salt bridge or some sort of porous barrier. Okay, here's a molecular view of what's going on, and we'll talk about some rules in a little bit. So here's the zinc, the electrons. If you're doing a direct solution, these electrons are given to copper ions. The copper ions, this is when we had them directly in contact with each other, turn into solid atoms, and the zinc becomes an ion. Okay, and now if you separate them, you've got the same process going on, except the electrons travel through the wire. So here's the little video.
When a strip of zinc metal is immersed in an aqueous copper 2 sulfate solution, electrons are transferred from zinc to the copper 2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc 2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown. The spontaneous copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper 2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper-2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode.
There we go. Okay, last topic for this podcast is the EMF, or the electromotive force of the cell. So the flow of electrons from anode to cathode is spontaneous. Electrons flow from anode to cathode because the cathode has a lower electrical potential energy. It's lower on the activity chart, is the way you would have thought of it so far. And the difference is measured in volts. So it's kind of like water flowing over a dam or over a waterfall. It's always going to go in one direction, from high potential energy to low potential energy. So it's the same way. Some atoms have high potential and some have low, and they always flow in one direction. And it's always called from the anode to the cathode. So 1 volt is the potential difference required to impart 1 joule of energy to a charge of 1 coulomb. So a volt is, I don't know where it went, there it is, 1 joule per coulomb. The EMF, the electromotive force, is the force required to push electrons through the external circuit. So the potential is called the EMF, E of the cell. And for 1 molar solutions, it's got a little standard symbol. Okay, those standard EMFs are measured by having every element's potential measured against the same element. In this case, it's hydrogen. Those are standard reduction potentials, and they are measured compared to the standard hydrogen electrode.
The cell potential of a voltaic cell, such as this zinc hydrogen cell, can be thought of as the sum of 2 half-cell potentials. Under standard conditions, the cell potential, E0, is the standard reduction potential of the cathode, minus the standard reduction potential of the anode. We can assign half-cell potentials once we settle on a reference half-cell potential. That has been chosen as the hydrogen half-cell, with 1 molar aqueous hydrogen ion and 1 atmosphere pressure of hydrogen gas. For the zinc hydrogen cell, the measured standard potential is 0.76 volts, and the standard half-cell potential for the cathodic half-cell is defined as 0. Thus, the standard half-cell potential for the anodic half-cell is minus 0.76 volts. This is the standard reduction potential for the reduction of zinc plus 2 ion. Now let's consider the silver hydrogen cell. In this case, the hydrogen half-cell is the anode. As before, the cell potential is the reduction potential for the cathode minus the reduction potential for the anode. Thus, the standard reduction potential for the silver-silver ion half-cell is 0.80 volts. Proceeding in this way, it is possible to measure and tabulate standard half-cell reduction potentials, such as these selected values. Remember that the standard half-cell potentials are always defined for the half-cell reaction written as a reduction. If the half-cell reaction is reversed, the sign of the standard potential is reversed.
All right. The EMF of the cell can be calculated from the E cell, which equals the reduction of the cathode minus the reduction of the anode. So when finishing your lab questions, you would use the table to find the reduction potential of the copper, which was the cathode, and subtract the reduction potential of the zinc, which was the anode. Let's stop there, and we'll practice doing cell EMFs and balancing equations in class on Monday. Hope you have a wonderful weekend, everyone. Talk to you soon.